Hi, today we're going to look at biological growth curve. This is our S-shaped curve, so we can represent it with our y-axis is going to be our population size. So we call that N, population size, and our x-axis is going to be time. So biological growth curve is going to tend to be an S-shaped curve like this. And we're going to be dividing it up into two halves. So we're going to first look at this first half here. Okay, so first half, and then we're going to look at the second half here. And you can see that these two halves have pretty different shapes. The first half is an exponential curve, and the second half is a logarithmic curve. So we're going to kind of divide this up because of these two different shapes. The whole S together is called the biological growth curve. If you already understand the exponential curve, then just skip this part. So let's start out with this exponential curve. It's also sometimes called the J-shaped curve. So I'm going to redraw it over here. So same axes always on this. So this is our J-shaped curve or our exponential curve. And what we're going to look at in what this curve is this curve is looking at dn over dt, which is how much bigger the population will be next generation. So change over time. So we could even say after the change in time that we're looking at. So whatever time frame we're looking at, and we're going to be looking at instantaneous change. This is without calculus, so we're not going to go into exactly how we calculate all of that. But for instantaneous change, we're basically looking at the slope of the line at any given moment. So that you notice the slope of the line changes. Over here, it's less steep. Over here, it's more steep. That's what our equation is going to model. So in general, we're going to see population growth when it's exploding, when it's in this exponential phase. We're going to see it be proportional to doubling, meaning it's going to double every generation. So for doubling, that's looking at this exponential part. Every generation, you expect to see about twice as many individuals as the last generation. It could be tripling, it could be 1.5-ing, but it's proportional to doubling. So we call it 2x type growth, where x is our starting number. This is 2 to the x type growth. I wrote this a little funky. Let me fix this so it doesn't look quite so bad. There we go. 2 to the x type growth. So where x is going to be our time. So this is just a type of curve that we see when we're seeing doubling are these exponential type curves. So what's going to happen is that in generation 1, you have 2 individuals. In the next generation, they reproduce to make 2 new individuals, plus maybe they're still there, or maybe they die and just produce 4 individuals. So in the next generation, we have our 4 plus 4 more. So we go 2, 4, 8, 16, etc. So this is our doubling type growth, which gives us this exponential curve. Okay, so our J-shaped curve. All right, and so we can see that here if we do generation 1 is here where we had 2 individuals. Generation 2, we now have 4 individuals. Generation 3, we're starting to go up a little faster now, 8 individuals. Generation 4, now we're going up really fast, 16 individuals. So the more individuals you have in your population, the faster the growth is going to happen, right? And so we're going to refer to this rate of change as R-inst. Okay, so R-inst, that is our rate of change. Okay, so we call this our growth rate. And the growth rate, to find out how much you changed over from one generation to the next, or how much you're changing over time to solve this equation, we're gonna multiply it by n. So we're gonna say that dn, our change in overall population size over time, how much bigger our population will be after time t, our dn over dt, this is gonna equal our growth rate times the starting population, right? And it's really important that we have that starting population in there because when you're at 2 individuals, if our growth rate is 2, we're multiplying 2 times 2 to get 4, okay? Now that we're at 4, we can't just go back to that number 2 again. We need to multiply it by our population size again. So now in the next generation, we're going to have 2 times 4, which is going to be 8. Next generation, 2 times 8, which will be 16. Next generation, 2 times 16, which will be 64. So that's why we keep this n term in here. So this is going to be our population size. This is going to be our growth rate. So I'm just writing growth rate because I already have growth rate up here. And this is going to be the change in population size over time. So change in size. Okay, so that's what all of these numbers mean. I'm going to just draw a little box around them. So you have all of your terms for this equation in one spot, and you can remind yourself what it means. All right, so that is our exponential curve that we're thinking about here. So now I want to move on to the logarithmic part of this because we're going to run into the problem of carrying capacity. Let me keep this down here for now. So K means carrying capacity. And that is how many individuals maximum a particular ecosystem can support, right? So that's our carrying capacity. Now, of course, when we hit carrying capacity, so let's put our K term up here. Sorry, I'm moving this around too much. So if this is K, right, remember this is N, our population size, and this is time on this axis here. So once our population size hits K, it's going to level off. So if that blue line is K, I'm going to draw a little white dotted line. If our population hits this, it's not going to be able to grow anymore because it's already at the maximum number of individuals that the population can support. Okay, so no growth here. So when n equals K, then we say that n at time 1 equals n at time 2. That means no growth, right? And so our dn over dt, our change in size over time, that's going to equal to 0. So that's the equation that we want. We want an equation where when n equals k, dn over dt equals 0. So what we're going to do is add on a term to the above equation to force this to happen. So how do we make r inst times n? What can we multiply that to make it into 0? Well, we can just multiply it by 0. That's our easiest solution. So if we want dn over dt equals r inst times n times mystery term to equal 0, all we have to do is make that mystery term equal to 0. So let's come up with a term that does just this. The term that we end up coming up with is this one, our new term. So our mystery term is going to be k minus n over k. Our carrying capacity minus the population size divided by our carrying capacity. Now this is going to get us 0 when k equals to n. So let's just change colors to solve for that one. So when k equals n, or when n equals k, just like I wrote up here, we want our whole thing to equal 0. So we get our dn over dt equals whatever r inst times n is, and we're going to plug in some numbers for this right now. Why not? So let's make, in our example, let's make r inst equal to 1. That would be strict doubling. So every generation, you have twice as many individuals as the generation before, as long as you're in exponential growth phase, you're nowhere near carrying capacity. And then we're going to have our n. Let's just start it out at 10. Okay. So these are our sample numbers to make everything easier to solve. All right, so here we've got our dn over dt, and we're going to say that k now is also equal to 10. So what if k equals to 10? So we have our r inst, that's 1, times n, which is 10, and that is going to be multiplied by k minus n over k. So k minus n is 10 minus 10 over 10, okay? So this is going to equal to 10 times, I should make my times like that, 10 minus 10 over 10, which is just 0. 10 times 0 is 0. So if we are at carrying capacity, this number is going to equal 0. So no growth over time, and we're at our nice flat line, just like that. But we know intuitively that as a population gets close to carrying capacity, it's gonna slow down. Its growth rate will slow. So it doesn't go to 0 all of a sudden, it slows down. So if you're in a crowded population, even if there's room for 10 more people, you're probably not gonna be, breeding a lot. So let's look to see what happens when we get close to K. So here we are back on our little graph. Here we're at the exponential part. And now I want to think about what happens when the population starts to get bigger and we start to get closer and closer to K. So this time let's make our K a little bit bigger. So this time let's make K equal to 20. So I'm going to do this one in green. So here we've got K equal to 20. We're going to keep our R inst equal to 1, meaning that this is doubling. So in our exponential part, our J curve, we're doubling our population every generation. And let's have our starting n be 10 again, because it was easy to multiply 10 times 1. All right, so let's see what's going to happen this generation here. So when we hit the magic number of n equals 10. So let's solve our equation. We've got our dn over dt. I'm going to rewrite the equation because I kind of lost it off my screen a little bit here. So dn over dt equals to r inst times n times our new magic term, k minus n over k. So let's plug in our numbers here. Actually, I'm going to change the color of this since this is our generic equation, not our special one. There we go. All right, so let's put our numbers in here. Oh, I forgot an equal sign. Not great. So here we've got our R inst, which is 1 times 10. And now we're not at carrying capacity because carrying capacity is 20. So we have 20 minus 10 over 20. Okay, so we've got 20 minus 10 over 20. That's 10 over 20, or 1/2. So we're going to have equals 10 times 1/2, which equals 5. So this is the amount of growth we expect to see in the next generation. We expect 5 more individuals. So we started with 10, we added 5 individuals to the population, so that gets us up to 15. If we were under doubling, if we were nowhere near carrying capacity, we would expect to see 10 additional individuals the next generation. So instead of getting 20, we're now getting 15. That's a slightly different number, right? So we have already slowed down our population growth. So let me put here for 10 where we're starting, and then here we'll put 15, 20, 25, 30, 35, and 40, right? We shouldn't get up to the 40, we should only get up to the 20. All right, so here we've hit 15, so we're already slowing down a little bit. Oh, let me get that in green. Okay, so here's our 15 for our next generation, right there. Okie doke. So let's do the next generation here. So now we have 15 individuals. We went up by 5. So now we are at n equals 15. So n equals 15. So that's going to equal our 1 times 10, which is 10, times 20 minus 15 over 20. All right. And so now this is going to equal to 5 over 20, which is 1/4. So we're going to have 10 times 1/4. Okay. And, excuse me. Oh my gosh. I put the 10 there by mistake. I'm so sorry. 15. I forgot we're starting with 15 now, right? Because we added to the population. The population did not stay the same size. Oh my goodness. Okay, 15. So 15 times 1/4, and that's going to equal to 3.75. So this is our growth in the next generation. I know that's not a whole number. It's close to 19, so we're going to plot it really close to the 20 over here. So one more generation out. Here was 1, 2, 3. Okay, so we're right about there. And now we are right here on our graph. All right, so now our population size in the first one was 15. Population size in the next one is going to be almost 19, 18.75. And so now we can do this for, let's do one more generation just for funsies. Let's do this one in red. And so now we're going to have n equals 18.75. I know that's not a real number, but we're just going to pretend maybe it's 1,875. Sure, it doesn't matter for us right now. So let's do this one more time. So 1 times 10, now times our magic number of 20 minus 18.75 divided by 20, okay? And so now our growth from generation blue to generation red is going to be this number. So 10 times 20 minus 18.75 over 20, which is going to be the total is going to be 1.172. Sorry, I wrote that down. Okay, so 10 times this mess, 20 minus 18.75 over 20. So this whole thing equals to 1.172. That's our growth. So that's how much bigger we're getting. So notice this. In this generation, we got 5 bigger. In this generation, we got 3.75 bigger. This generation, we got 1.172 bigger. So every generation, we're getting bigger by just a little teeny tiny bit. Okay, so now we're at our total population size of 19.92. So we're just about at 20. And we know what happens when we actually hit 20. We get 0 growth, okay? And so we're going to get to really close to 20, and then it's just going to start to level off. So that's what we see here. Okay, so that is where we get that logarithmic part of this curve, is as we approach carrying capacity, the growth rate, dn over dt, slows down. All right, I hope that was helpful. If you have any questions about this, please let me know and I'll try to answer them.